During this fourth module, we go into details about the properties of electromagnetic interactions. In this third video, we discuss the phenomenon of spin and its consequences for electromagnetic interactions. After following this video, you will know a spin as a typical quantum observable and its measurable consequences, and the functional principle of a penning trap. We have seen in video 1.1 that the matter particles known up to now are all fermions with spin 1/2. The particles carrying no forces are spin 1 bosons. The only elementary scalar boson observed to date is the Higgs boson. It is therefore inevitable that we discuss spin in more depth. We will not do that with a formal approach. Instead, we discuss only the consequences of spin. Spin is a typical quantum observable which has no classical equivalent. It is an intrinsic degree of freedom corresponding to an angular momentum manifesting itself by a magnetic moment. There is no movement associated to either of these moments, let alone a rotation. This is evident because spin is a property of point-like particles. We will nevertheless use a classical analogy laid out on this slide. For a particle with charge q and mass m, the magnetic moment mu is related to the angular momentum L by mu equal to q divided by 2m times L. This is easy to see for a particle traveling on a circle of radius r. Its magnetic moment is the product of the current caused by the motion and the surface included in the path. The current can be expressed using charge and angular velocity. The magnetic moment is thus proportional to the angular momentum. The proportionality factor is simply q divided by 2m. It is plausible that an intrinsic angular momentum will cause an analogous magnetic moment. A new proportionality constant comes in. It's called the geomagnetic ratio, G. Its value depends on the internal structure of the particle. For a point-like fermion, such as the electron, muon or tau, the spin is 1/2, the charge is minus e, so mu is equal to minus g times e divided by 4m. A QED calculation to first order gives g simply equal to 2. The classical experiment to measure g uses an electron trapped in an electromagnetic bottle called a penning trap. A very good description is available in the article by Ekstrom and Vineland in Scientific American that is quoted on the bottom of this page. The system resembles a macroscopic atom, where the nucleus is replaced by an external field. The electron circulates in a magnetic field, which is pretty much homogeneous except for the focusing component generated by a ferromagnetic nickel ring in the equatorial plane. An electric field counteracts excursions along the axis of the magnetic field. It is generated by a ring electrode and 2 cap electrodes. We calculate the energy levels of such a system in video 4.3a. The result, which is given here, neglecting the focusing effects of the ring and the caps, is relatively simple. The first term in blue corresponds to a free movement in the z direction. This movement is constrained by the focusing components we have neglected. They cause the actual oscillation. The 2 terms in red correspond to a harmonic oscillator in the equatorial plane with energy eigenvalues which are omega times n plus 1/2 for n equal to 0, 1, 2, and so on. Adding the magnetic moment of the spin, mu, the last term in green is obtained. The 2 directions of spin, Sz equal plus 1/2 and minus 1/2, are therefore separated by the same energy difference omega as the main levels, provided that g is exactly equal to 2. The energy levels for spin parallel and anti-parallel to z would then be displaced by exactly 1 step omega. This degeneracy does not exist if the value of g differs from 2. The levels are then slightly displaced by a frequency shift delta omega, equal to omega times g minus 2 over 2, which can be measured with impressive accuracy using a penning trap. The principle of the measurement is shown here by its electrical analog. In an empty trap, The three electrodes form a capacitance network that transmits the AC signal generated on top to the detector on the bottom. The trapped electron introduces an additional capacitance inductance in this circuit. The amplitude of the transmitted signal as a function of frequency thus indicates the number of electrons in the device and the frequency shift delta omega, which determines the deviation of G from 2. The figure on the left shows the detected signal as a function of time at a well-adjusted frequency. Each major step corresponds to the loss of one electron in the trap. The right figure shows the frequency shift delta omega as a function of time. Its two minima indicate the two directions of spin. Also indicated are the much larger shifts due to a change in orbit. The precision of the experimental result is amazing. You see the value obtained in blue on the bottom of the page. The value in bracket indicates the measurement error, which applies to the 13th and 14th decimal places. Comparison of this value to electromagnetic theory requires a calculation of the same quantity to 10th order in the perturbation expansion. One finds good agreement between measurement and theory even at this unrivaled position. The measurement also gives us one of the most precise values of the fine structure constant alpha equal e squared divided by 4 pi. In the next video, Mercedes will discuss Compton scattering, the elastic scattering of a photon of an electron.